We are going to start notes on day 5 of factoring, and today's factoring goals are to work with some special cases of factoring. So these are some shortcut special cases that you could also do by guessing and checking, but if you recognize when you have one of these, there'll be a quicker way to go ahead and factor it. So the first special case, still on the same section of factoring, is called the difference of two squares. You'll see me abbreviate this later in the year as a D2S, difference of two perfect squares. So difference, think subtraction, the operation of subtraction, and two squares means these are binomials in which both terms have to be perfect square values. So perfect squares, 1, 4, 9, 16, 25, etc. You got to have those perfect square values. And later when we do this strategy with polynomials, we'll talk about how the exponent needs to be an even. But since we're just working with quadratics right now, it'll just have an x squared in it. There's a formula that I'm going to write down, and it says a squared minus b squared. And this is always going to factor into two factors that are almost identical except for their signs, 1 plus, 1 minus, and then you square root each of the terms. So when you square root a squared, you just get a and a. When you square root b squared, you get b and b. So the factors, again, almost the same, except they differ in signs. You'll later hear this being referred to as those are conjugates of one another. So the best way to go ahead and understand it is to practice it. So we're going to factor all of these examples. Here is our first one, 4x squared minus 9. So you will notice that 4 is a perfect square, 9 is a perfect square, the x is being squared, and it is subtraction of two terms. So if we set up our factors, we square root each term. So the square root of 4x squared will be 2x and 2x. Square root of 9 is 3 and 3. And 1 positive, 1 negative, because a positive times a negative will give you that negative 9 that we need. That's pretty much all there is to the difference of two squares. Hardest part is recognizing when you have them. But if you don't recognize you have it, you could always guess and check, find the factors of A, find the factors of C, and in this case, when you're checking, you want a B value of 0. So they would have to cancel out because there is no B term in these problems. Okay, see if you guys can try this one on your own. After I write it down, go ahead and hit pause. 36x squared minus 49. Try that one. As I go through this, setting up my factors, 1 plus, 1 minus, square root each of them. 6x, 6x, 7, 7. There's my factors. Okay, we did work a lot with factors when we did graphing in intercept form. Factors are useful because they can help you find the x-intercepts. And later on in this unit, you will see more of that connection between the factors and the zeros, the factors and the x-intercepts of a graph, of a function, how they relate to each other. Let's try this one together just because it is a little different, 5x squared minus 20. At first glance, you're probably going to say this is not a difference of two squares because 5 and 20 are not perfect squares. However, you should notice that there is a GCF of 5. And remember, the GCF is always the first thing you take care of. So if we factor out a 5, dividing both terms by 5, that leaves you with x squared minus 4. The x squared minus 4 part is a difference of two perfect squares. I'm going to bring down my GCF of 5 and set up my two binomial factors and square root each term to get x, 2, 2, 1 plus, 1 minus. Okay. Here's another one that I would like you guys to try on your own. Don't get tricked. There is a twist to it, so don't think it's easier than what you think here. 25x squared minus 100. So pause, think about it, check your answer with mine. Although these are both perfect squares right now, I could factor it, but then my factors could be factored further. Unless you notice 25 is technically the GCF of this problem. You should be pulling out a 25 from both terms. And then again, you get that same d2s of x squared minus 4. So x plus 2 and x minus 2 again. If you did not recognize that there was a GCF in the beginning, you could factor it using the difference of two squares strategy, and you would get 5x plus 10 and 5x minus 10. But you would notice, or I would want you guys to notice, is that each of these factors still has a GCF. I can pull a 5 out of here and a 5 out of here. So when I factor out a 5 from the first one and a 5 from the second one, those would get multiplied to become 25. And if you factored out the 5 from the first one, it would leave you with x plus 2. And when you factored out the 5 from the second one, you would get x minus 2. So you can still get the same answer, but most students are more likely to do and remember the GCF first rather than do it at the end of the problem. So it's easier to do the GCF in the beginning rather than at the end. And this is our last difference of two squares example before I teach you one other shortcut. Okay, we have 121x squared plus 1. Think about that for a minute and check. So this one was kind of a trick question. This is not a difference of two squares because of the addition sign. This is not factorable. The only way that we can factor a quadratic is with only two terms, so a quadratic binomial is if a GCF exists or if it is a difference of two squares or the combination of both. This is not either. There is no GCF other than one, and this is not a difference of two squares, so therefore it cannot be factored. The next factoring shortcut is called factoring perfect squares trinomials, or perfect square trinomials. And I will abbreviate these as PSTs, perfect square trinomials. Again, I'm going to put up the formula and then explain how it works with some examples. These trinomials could still be factored by guessing and checking, the grouping method that you did the other day. However, if you recognize when you have them, there is the shortcut method. So the first form looks like this. There's two formulas depending on the sign. A squared plus 2ab plus b squared. And the other one is a squared minus 2ab plus b squared. So the only difference is the sign of your middle term. The a squared and the b squared are referring to the fact that the first term and the last term, they need to be perfect squares. So those numbers again, 1, 4, 9, 16, 25, etc. The last term is always positive. So you'll notice these are pluses here. But the sign of the middle could change. And to verify the 2ab, I will show that through an example. What this is just saying is if you square root the first term and the last term, multiply those and double it, it should give you the middle b term. But I think it'll make more sense with an example rather than this formula. When we factor these, the factors are identical. Nothing is different about them. So for the first one, it would be a plus b times a plus b. Okay, you're square rooting the first and the last terms, just like we did with a difference of two squares, and we take the sign of the middle. Or, since the factors are identical, you could write it as a plus b squared. You have two of them. The difference with the second formula, because the middle term is negative, that means we're going to have a minus b for both, or a minus b to the second power. It's called the square of a binomial. We're squaring a binomial factor. So if we put this into practice, I'll show you how it works. I gave you x squared plus 12x plus 36. I could factor by guessing and checking, finding the factors of 36 that add to 12 because the a value is 1, or I can try this new strategy. The a value is 1, that's a perfect square. The c value is 36, and it's a positive, that's a perfect square. But to make sure this is a PST, you have to check the middle. So to see if the middle works out, this is what you do. You square root the a value, which is 1. You square root the c value, which is 36, to get 6. You multiply them together, and this stays 6, and then you double it, and you get 12. That matches. That verifies that this is, in fact, a perfect square trinomial. So you should know now that the factors are going to be identical. So you square root the first term and the last term and take the sign of the middle. So we're going to have 1x plus 6. You could either write it twice or write it as the square of a binomial. This checking part that I wrote here in the middle is just to verify that we even have a PST. Because if it's not a PST, then you can't factor it using these shortcut strategies. Here's another one. 49r squared minus 14r plus 1. So right off the bat, 49 is a perfect square, 1 is a perfect square. So you might be thinking, oh, shortcut, but we got to check the middle. So you square root the 49, you square root the 1, you multiply them, and you double it. Now here when I double it, I'm getting positive 14, and that's okay. We're not trying to verify the sign, we're just trying to verify the value. So 14 is good enough to verify that this is in fact a perfect square trinomial. So factors are identical. Square root the a and the c again to get 7r and a 1, and you take the sign of the middle term. They're both the same, so you can either write it twice or square that factor. I'll accept either or. Okay, why don't you guys go ahead and try this one on your own. All right, hit pause, check to see if it's a perfect square trinomial first, and then factor it, and look, unpause to see my answer. So first glance, I think it's a perfect square trinomial because 9 and 16 are perfect squares. I just got to test the middle. Square root of 9 is 3. Square root of 16 is 4. I'm going to multiply those together to get 12 and double it, and I get 24. That does match up. So my factors are identical. Square root the first and last, and I will get 3x minus 4 because I'm getting the sign of the middle. If I were to redistribute this out, like 3x minus 4 times another 3x minus 4, you will end up getting this middle term of negative 24x. So even though you're not using the negative 24x to help you factor, it will be present if you redistribute your factors out. Okay, here's another one. Try this. 144x squared plus 120x plus 25. You'll see on this one before you hit pause that these numbers are really big. You probably don't want to be sitting here and guessing and checking all the factors of 144 and 25 that could give you a b value of 120. That's a lot right there. So go ahead, try that, and pause it and check my answer. I'm just going to verify that it's a PST. Square root the first, square root the last, multiply them, double it. So we're good. So my factors will be 12x plus 5 and another 12x plus 5. Next one, 2x squared minus 32x plus 128. This one we're going to do together. These are all even values, so right off the bat, you should know there is a GCF in this example of 2. So I'm going to factor that out first, especially because 2 and 128 aren't perfect squares, so I can't use the shortcut strategy. And that's going to be 64 when you divide that by 2. Now this in the center is going to be a perfect square trinomial. And you could test it out. Square root of 1 is 1. Square root of 64 is 8. Multiply them, double it, gives you 16. Don't forget to bring down your GCF of 2 when you're factoring. And then you're going to have x minus 8 squared. Both factors are x minus 8. And this is the last one of this type. We're on example 6. 100x squared plus 3x plus 49. Go ahead and pause it and check if it is a PST first before anything else. If I check if this is a perfect square trinomial, because 149, they're both perfect squares, I'm going to get 10 times 7, which is 70, and if I double that, I get 140. That doesn't work. That's not 3. So this is not a perfect square trinomial. You could sit here guessing and checking all day long, finding factors of 100 and factors of 49. That'll give you 3. There aren't going to be any that work. This problem is not factorable. You'll learn about this more in a couple sections from now, but if you're ever struggling to factor something and wondering whether it was even factorable in the first place, you could do the discriminant test, which you probably don't know what that is right now. It's part of that big long formula that you learned in Algebra 1. So the b squared minus 4ac is the part that's underneath the radical. And if you do the discriminant and you get a perfect square, like 1, 4, 9, 16, that means your problem was factorable. So if I do my discriminant real quick, b squared, so that's 3 squared, minus 4 times 100 times 49, I'm going to get 9 minus a really big number, which will be negative, automatically meaning it's not a perfect square. 400 times 49 is 19,600. And if you subtract, you're going to get negative 19,591. This is not a perfect square. It's negative, and plus 19,591 is not a perfect square. If you square root that, you'll get a decimal. So therefore, because it's not a perfect square, this is not factorable. Say you did the discriminant and you got positive 36. That would mean it was factorable, and you should keep guessing and checking until it works. So that's just another tidbit that you'll learn more about later this unit that might help you while you are factoring. Now that you guys have learned all the methods, you're going to get just a quick little summary of factoring strategies. I'm going to pull that up here. It's going to just take me a quick second. In Unit 2, factoring, all our methods. So you should be getting this handout that just summarizes everything we've been working on. And it's broken up by the number of terms. Also, you'll notice the top sentence says, before you start to factor, always check to see if there is a GCF. First step, no matter how many terms there are. So when there are 2 or more terms, one method is always looking for the GCF. There's an example of that all to the right. If there are just 2 terms and it's not a GCF problem, then the only way we factor it is by a difference of 2 perfect squares. And there's an example. And then it goes into the 3 terms. So there's 3 boxes on that, depending on what type it falls into. So there's the guessing and checking with 3 terms. So that's when the A value is 1, or the A value is not 1, but the A and C don't have a lot of factors. So when A is 1, we find factors of C that add to B. And when the A is not 1, we have to find factors of A and C that when you multiply, they will add to B. And you have to always check your outer and inner terms to make sure you're factoring correctly. And there's an example to the right. Then there was the longer factoring strategy if A and C have lots of factor options and guessing and checking is not working, and that's the grouping method. The example over here, technically, A and C don't have a lot of factors, so that would be a problem that I would expect you do by guessing and checking, not the grouping, but I just provided an example of how grouping works using that problem. But that would be a problem that you should guess and check, not use grouping. And then the last one with 3 terms is what we just learned today, the perfect squared trinomials, and it provides another worked out example of what we just did. I'm going to have you guys hit pause on this video. There is going to be one other part to the video, but it has to do with day 7's lesson. So tomorrow you guys are going to work on a factoring type 3. If you want to get a head start on it tonight and copies are made, you can, because it is a longer type 3 assignment. But the more you practice factoring, the quicker you get at it. And then the day after that, you guys will have a quiz the last 20 minutes. And there will be intervention worksheets created for those of you who get lower than a 75, just because factoring is such an important skill. And on that day, when you guys take the quiz, you'll get a little bit more time to work on the type 3, maybe another 15, 20 minutes. So you'll get 2 nights to do the type 3. And then there's also one other example that we're going to do that day, which will be part of this video right now. So hit pause, because this last example is going to be part of day 7's lesson. Okay, so beginning of day 7, there's no warm-up today, but I want to present and have you guys think about this question, because there's a question similar to it on your type 3s that you were working on yesterday. Okay, I just want to see real quick where time's at in terms of the recording. All right. So I'm going to pose this, and I do want you to write it in your notebooks. What can the value of C be in this quadratic trinomial? So if I gave you x squared plus bx plus 18 in order to make this factorable. So what could the b value become if this was factorable? So I'm going to give you guys a couple minutes to think about it on your own. I'm going to hit pause, and then we'll brainstorm together. So looking at it, I know because the a value is 1, that the factors of C will add to the b. So you should start off by finding factors of C. 1 and 18, 2 and 9, and 3 and 6. Therefore, if I add those together, they'll give me my b values. And I'm saying adding because the C term is positive, so I know my signs are going to be the same in my factors, so they're going to be added together in a positive direction or added together in a negative direction. So one possible outcome for the b value is 19, because 1 plus 18 is 19. Another combination would be 11, because 2 plus 9 is 11. And the last combination would be 9, because 3 plus 6 is 9. These are not the only answers, though. B could be a negative value. So I could still add those together, but make it negative. Well, both of them negative, because a negative times a negative would still give you this positive 18. So negative 1 and negative 18 would give you negative 19 as a middle term. And you could do that with the last two as well. Negative 2 and negative 9 would give you negative 11 as a b, and negative 3 and negative 6 would give you negative 9. The two negatives will multiply to a positive, but add up to a negative to give you a negative middle term. So that's how you do that one, and there are questions similar to that on the type 3 that you guys will get a little more class time to work on, and the last 20 minutes will be the factoring quiz. Remember, you guys really need to study on this factoring, because if you don't do well, you will get some supplemental intervention worksheets, because we've got to master this skill. That's it for today.